Have you ever wondered how they calculate a home run's distance before the ball even lands? Or how a rocket's path is plotted with just insane accuracy? Well, that's not magic. It's physics. Specifically, it's kinematics, the language of motion. So let's dive in and figure out how to describe the journey of pretty much anything that moves.
All right, here's our game plan. We're going to build this whole thing from the ground up. We'll start with this super simple question. Where is something? Then we'll bring time into the picture to talk about speed and its cousin, velocity. After that, we'll get into how motion changes. And finally, we'll unlock the 4 power equations that let you predict motion like a pro, even with something as huge as gravity.
So, first things first, where are we going? I mean, before we can even think about how fast something is moving, we have to agree on where it is and where it's been. This is the absolute bedrock of kinematics, so let's nail this down. Okay, let's start with a word we all know, distance. This is basically your car's odometer or the step counter on your watch. It just adds up every single step, every twist, every turn of your entire journey. That's it. In physics, we call this a scalar. It's just a number, no direction, nothing fancy. But, physicists like to be a little more precise. And that's where displacement comes in. See, displacement couldn't care less about the scenic route you took. It only cares about the shortest, straightest line from your starting point to your finishing point. And because that line points somewhere, it has a direction. We call that a vector.
Now, to really see the difference, just picture yourself running one lap around a 400-meter track. Your distance is, pretty obviously, 400 meters. Your legs will definitely feel those 400 meters. But what's your displacement? Well, you ended up in the exact same spot you started, right? So your displacement is 0, a big fat 0. That one idea is absolutely crucial for everything we're about to cover.
Okay, part 2, speed versus velocity. We figured out how to talk about a change in location. But a journey isn't just about where you go, it's also about how long it takes you to get there. So it's about time we added, well, time.
Average speed is the one you already use every day without even thinking about it. You just take the total distance you traveled, our full 400-meter lap for instance, and you divide it by how long it took. Super simple. It gives you one number that tells you, on average, how fast you were going.
Average velocity, on the other hand, uses displacement. So think back to our track runner. After that one full lap, their displacement was 0, remember? So if we divide 0 by the time it took, their average velocity for the whole lap is also 0. Sounds totally weird, I know, but it's true, because from a physics point of view, they didn't actually end up anywhere new.
So here's the bottom line. Speed is a scalar. It's just a number on your speedometer. It tells you how fast. Velocity, though, is a vector. It tells you how fast and in what direction. So saying you're going 60 miles per hour, that's a speed. Saying you're going 60 miles per hour north, now that's a velocity.
All right, section 3, the rate of change. Things in the real world almost never move at a perfectly steady speed. They speed up, they slow down, they turn corners. The physics word for any of those changes is acceleration, and it probably doesn't mean quite what you think it means. See, in physics, acceleration isn't just about stomping on the gas pedal. It's defined as the rate of change of velocity, and that's the key word there, velocity. This formula just says acceleration, A, is the change in velocity, that's what the little triangle delta V means, divided by the change in time. Because velocity includes direction, you are accelerating if you speed up, slow down, or just change direction.
So yeah, there are actually 3 ways to accelerate. Speeding up, that's the obvious one. Slowing down, which physicists just call negative acceleration, and then there's the one that trips people up, changing direction. Seriously, even if your speedometer is locked at 30 miles per hour, the second you turn that steering wheel, you are accelerating, because your velocity, your direction, is changing. Okay, this is where it gets really good. Section 4, the 4 power equations. We've got our building blocks now, displacement, velocity, and acceleration. Now it's time to put them all together. If we have one special condition, constant acceleration, we can use 4 amazing equations to literally predict the future of a moving object.
Meet the big 4. These are the kinematic equations. Honestly, you should think of these as a physicist's secret toolkit. If you know just 3 little things about an object's motion, you can use one of these babies to find out everything else, where it's going, how fast it'll be going, you name it.
Now don't get bogged down by the formulas themselves. Look at the column on the right. Missing variable. That is the secret key to all of this. It tells you exactly which equation to grab.
For example, if you're trying to solve a problem and it doesn't say a single word about displacement, you instantly know to use that first equation. It turns a complex problem into a simple matching game. It's awesome. So for our last section, let's talk about gravity. Now you might be thinking, okay, those equations are cool, but when is acceleration ever really constant in the real world? Well, my friend, it is happening all around us all the time. It's the force that's literally holding you in your chair right now, gravity.
Right here on planet Earth, any object that's in free fall, and for now, let's just pretend there's no air resistance, accelerates downward at a constant 9.8 meters per second squared. What that means is for every single second an object is falling, its speed increases by another 9.8 meters per second. That number, which we call g, is a cornerstone of physics.
And this constant pull of gravity leads to a truly mind-bending idea. Gravity is the great equalizer. If you were in a vacuum, so no air to get in the way, and you dropped a heavy bowling ball and a light little feather from the exact same height, they would accelerate at the exact same rate and hit the ground at the exact same time. Wild, right?
So, that's the whole journey in a nutshell. We started with displacement to figure out where something is. We added time to get velocity, to know how fast it's moving and in what direction. And we finished with acceleration to describe how that motion changes. And all together, these concepts create the complete language of kinematics. So now we have this amazing power to describe how things move. But kinematics only ever answers how. It never answers the biggest question of all, why? What was the push or the pull that made the object move in the first place? Well, that's a story for another time. Thanks for joining this explainer.